3I Atlas didn't just pass through our solar system, it changed inside it. When the European Space Agency quietly released a delayed batch of calibration data, what appeared first was nothing more than a blurred green haze. But beneath that haze, a pattern emerged. A geometry that should not exist in a natural comet. Symmetry where there should be turbulence. A pulse where there should be silence. Before we go deeper, subscribe if you're new here and tell me in the comments where you're watching from and what time it is right now. I'm mapping every point in time when this story first reached you. Here's what we've learned since the veil was lifted frame by frame on an object that refuses to behave like stone, gas, or ice. An object that bends the simplest laws of motion, light, and heat, and in doing so, bends our sense of what is natural. It began, as most discoveries do, with something that was never supposed to be noticed. At 4:26 UTC on October 3rd, 2025, a calibration frame from the Trace Gas Orbiter was automatically uploaded into the European Space Agency's internal archive. The image was not scheduled for analysis. It wasn't even meant to be public. It was part of a background test, a low-priority exposure used to fine-tune the infrared optics of the orbiter. Every week, hundreds of similar calibration shots were stored and forgotten. This one should have been too, but when a young analyst named Felix Morvan at the ESA's Mission Operations Center in Darmstadt reviewed the file, he paused. The frame showed the faint outline of the green glowing coma of 3I Atlas. At first glance, it was unremarkable, a soft blur against a field of distant stars, but buried within that blur was a narrow curved ridge of light running perfectly along the center of the comet's core. It wasn't random, and it wasn't an imaging glitch. Morvan enhanced the exposure using a false color overlay to remove solar backscatter. What emerged from the darkness was a symmetrical arc. Smooth, consistent, and far too precise to belong to the chaotic world of ice and dust. Comets are irregular by nature, fractured by solar radiation and rotation. Nothing about them forms straight lines or mirrored structures, yet here was an internal reflection so clean it could be traced mathematically. He ran the frame through the anomaly filtering algorithms used to identify diffraction artifacts. None matched. The glow persisted under every test. When the team cross-checked the data against an image taken by Mars Express hours earlier, the same ridge appeared identical in position and curvature. The probability of two separate instruments generating the same false geometry was nearly zero. The structure was real. Inside the science division, the find caused quiet unease. The pattern looked engineered. Some compared it to a rib or a supporting spine, the kind of feature found in architecture, not geology. Others argued it could be a frozen jet, a tunnel where gas once vented before freezing solid, but even that failed under scrutiny. The ridge's reflective profile was too uniform, its luminosity constant along the entire length. Nature does not build with symmetry like this, at least not in the vacuum of space. When the brightness data was converted into a 3D model, a more startling detail appeared. The ridge wasn't on the surface, it was embedded inside the comet, beneath a translucent layer of volatile material. That meant whatever it was, it had to conduct or reflect light internally, like a fiber optic thread running through stone. Materials that can do this are crystalline or metallic, but neither should exist in stable form within a cometary nucleus. Over the next 48 hours, ESA engineers used adaptive phase mapping to measure the light curve along the ridge. Its reflection profile did not behave like dust or ice, it behaved like a single surface, continuous and polished at microscopic scale. It reflected narrowband light in coherent intervals, the kind produced only when light interacts with ordered molecular structures. The conclusion was inescapable. 3I Atlas contained a feature that mimicked engineered material. By the end of the week, the calibration frame had been reclassified as a high-priority observation. It was quietly removed from the public archive and placed under internal review. A note in the system log read only, "Potential artificial geometry verification pending." It was supposed to be a routine image, a fragment of background data destined for deletion. Instead, it became the first frame to challenge the assumption that 3I Atlas was just a comet. And from that single photograph, a new question emerged. If this ridge was built, then by what? And when? When the first reports of fluctuating brightness arrived, nobody at the European Space Agency paid much attention. Variable luminosity was common among active comets, caused by rotation, by dust jets, by sunlight striking different surfaces. But the case of 3I Atlas refused to fit the pattern. The fluctuations were not random. They followed a rhythm so precise that it could be measured against the ticking of an atomic clock. At first, it was the Las Campanas Observatory in Chile that noticed it. Astronomers tracking the comet's green coma with high-sensitivity CCDs saw its brightness rise and fall over a period of roughly 11 hours. They assumed it was a simple rotation cycle until the pattern repeated perfectly across 3 consecutive nights. Every peak, every trough, every amplitude was identical to the decimal point. Nature makes symmetry, but it doesn't make metronomes. The observatory sent their data to ESA's astrophysical division in Darmstadt. There, the light curve was matched against observations from Mars Express and the James Webb Space Telescope. The result was shocking. Webb's infrared sensors detected the same pulse, but not as reflected light. The rhythm came from heat signatures, thermal oscillations that radiated from within the object. The surface was cold, but something beneath it warmed and cooled on schedule. As though energy were being released and absorbed from the inside out, the discovery sparked a quiet storm within ESA. Scientists ran through every natural explanation they could imagine. Could it be internal pressure from sublimating gases? Could cavities in the nucleus expand and contract in a timed cycle? The thermodynamic models said no. The temperature of the nucleus was too stable, and the cycle too exact. There was no known process that could produce such clean periodicity in a natural body. Some theorized that 3I Atlas might contain a trapped reservoir of volatile compounds, venting through a single fracture, but that would create asymmetric jets, not global pulses. And even if a vent opened and closed rhythmically, it would need a regulating mechanism. In nature, there is none. Webb's deeper thermal scans added another layer of strangeness. The peaks of the pulse showed no delay between different wavelengths. That means the energy source wasn't propagating outward like a normal thermal wave. It was radiating everywhere at once, uniformly. It was as if the entire interior of the comet flickered, then dimmed, like a single system switching on and off. ESA data engineers began calling it the heartbeat. Not officially, of course in reports. It was listed as a volumetric luminosity oscillation, but within the labs, the nickname stuck. Every 11 hours and 12 minutes, 3I Atlas blinked. When the pattern held across a dozen consecutive cycles, skepticism gave way to discomfort. Planetary scientists compared it to pulsed emissions seen in pulsars and magnetars, except those are stars, not small icy objects less than a kilometer wide. Some tried to fit the data to a harmonic resonance model. Maybe the object's internal cavities resonated like an organ pipe, but the frequency was too low for sound waves and too stable for geological motion. The final confirmation came from independent teams in Australia and Japan. Using time-lapse imaging, they recorded the glow fading and returning at the exact same rate observed from ESA and Webb. The pulse was real, global, and synchronized across multiple instruments separated by thousands of kilometers. By late October, the heartbeat of 3I Atlas had entered official mission notes. The file name in ESA's internal database read, Object 3, I divided by Atlas, periodic luminosity event, sustained. No explanation was attached. Whatever caused the pulse wasn't slowing down, weakening, or randomizing. It was steady, patient, precise, and indifferent to every theory thrown at it. And for the first time, scientists began to ask not what was pulsing, but why it was keeping time at all. The first person to describe it as breathing wasn't a scientist. It was an amateur astronomer from Wellington, New Zealand, who had been stacking long exposure images of 3I Atlas over several nights. When he overlaid the frames, he noticed that the diffuse green clouds surrounding the comet seemed to grow and shrink in a slow, steady rhythm. At first, he thought it was an artifact, maybe a tracking error, or a change in sky transparency. But when he corrected for both, the rhythm remained. The coma itself was expanding and contracting. In a normal comet, the coma, the halo of gas and dust around the nucleus, is chaotic. Jets erupt from random vents, solar radiation pushes particles outward, and gravity pulls them back. The result is a shimmering, turbulent glow that constantly changes shape. But in the case of 3I Atlas, Every frame told the same story. An even global expansion that reached its maximum size every 11 hours and 12 minutes, perfectly synchronized with the light pulse discovered weeks earlier. When the observation reached the European Space Agency, the reaction was mixed. Some dismissed it as a coincidence, a trick of exposure timing. Others realized that the timing was too precise to be random. To test it, the Mars Express orbiter captured a series of high-speed imaging bursts during one complete cycle. The results confirmed what the amateurs had seen. The Coma swelled by nearly 2% in radius, then contracted back to its original size, following the same pulse period to the second. ESA's gas dynamics team attempted to model the process. They assumed that periodic outgassing from the nucleus could push the Coma outward like a heartbeat of vapor. But there was a problem: no new gas appeared. The spectrometers detected no spike in CO2, H2O, or any other volatile compounds during the expansion phase. The Coma's composition remained constant, while its density changed. In simple terms, the glow brightened and stretched, but nothing new was being added to it. To produce that effect without new material, something had to be redistributing energy through the Coma itself. When analysts filtered the data through Doppler shift algorithms, they found minute velocity variations. The particles were accelerating outward, then slowing down again, as if an invisible pressure wave was rippling through the cloud. This wave wasn't random turbulence. It moved in perfect spherical symmetry, originating from the center of the nucleus and propagating outward. One explanation, the resonance model, suggested that temperature gradients inside the comet could cause rhythmic expansion of trapped gases, much like a deep exhalation through hidden pores. But when thermal maps from the James Webb Telescope were compared to this model, the data didn't fit. The temperature of the core changed by less than half a degree between pulses far too small to drive such large movements. Another theory proposed that solar wind fluctuations might be compressing the Coma externally, creating the illusion of breathing. Yet when the solar wind was steady, the rhythm continued unchanged. Whatever the cause, it came from within the object, not from the Sunday. By mid-October, researchers began to talk privately about coherent energy transfer. The Coma wasn't venting, it was responding, as if each particle was receiving a synchronized signal telling it when to move. Magnetic readings hinted at a faint oscillating field enveloping the entire structure. The field's strength peaked at the same moments as the expansion. It wasn't strong enough to move dust mechanically, but strong enough to align charged particles. That alignment could, in theory, change the way the Coma scatters light, making it appear to breathe. If this were true, 3I Atlas was doing something no natural comet has ever done, coordinating its own atmosphere. When the dataset was finally reviewed in Darmstadt, one senior analyst wrote a short line in his log before the file was locked for internal study. The Coma behaves as a single system, not as debris. The phrase spread quietly among the teams. The comet was no longer just glowing. It was responding, expanding, and contracting with impossible precision. A natural object can sublimate, vent, or fragment, but it cannot breathe. Yet 3I Atlas did. Every 11 hours and 12 minutes, with mechanical regularity, it took another breath in the dark. The first signs came from an unexpected corner of the European Southern Observatory in Chile. Using the VLT's high-resolution spectrograph, a small research team noticed that one of 3I Atlas's spectral lines was unusually sharp and bright, a narrow emission band near 341 nanometers that matched neutral nickel. At first, this wasn't considered remarkable. Many comets and asteroids contain trace amounts of nickel, often buried within their metallic cores, but as the team continued analyzing the data, something was missing: the corresponding lines of iron. In the known universe, nickel and iron are inseparable twins. They are forged together in the furnaces of dying stars, created when atomic nuclei fuse in the final seconds before a supernova tears the star apart. The explosion scatters them evenly, bonding them into the same grains of cosmic dust that will one day form planets, moons, and comets. Wherever astronomers detect nickel, they always detect iron. The ratio may vary, but one never appears without the other. Until now, when the data from Chile was shared with other observatories, including Subaru in Hawaii and Gemini South, the pattern repeated. The signature of nickel glowed brightly across several wavelengths, but every iron marker was gone. The simplest explanation was an instrument calibration error, perhaps caused by the sun's angle or a sensor defect. The Japanese team even recalibrated their optics, assuming their data was faulty. Yet each recheck confirmed the same result: strong nickel, no iron. By early October, the anomaly was verified independently by Mars Express spectrometry. Its onboard instruments, designed to measure trace gases around Mars, detected vaporized nickel atoms in the thin trail of 3I Atlas's Coma. The readings showed nickel in a gaseous, ionized state, pure, unbound, and drifting like metallic vapor. But even at those temperatures and distances from the Sun, iron should have sublimated first. Iron is more volatile under solar heating. It should have appeared long before nickel. Its total absence made no sense. ESA analysts proposed the thermal selection hypothesis, that heat within the comet might have separated the two elements through layered sublimation. But to achieve that level of separation, the nucleus would need to reach thousands of degrees Celsius, enough to melt and reshape its entire core. The infrared readings, however, showed no such heating. The surface temperature of 3I Atlas never rose above 160 Kelvin, colder than liquid nitrogen. Then came the discovery that shifted the tone of every internal report. The nickel signal wasn't just pure, it was stable. Across repeated scans, the strength of the spectral line did not decay. It fluctuated gently, in rhythm with the same 11-hour pulse that governed the comet's brightness and Coma expansion. Somehow, the nickel vapor was being replenished in perfect phase with the object's internal cycle. It wasn't boiling away, it was being released. If this was simple outgassing, the emission lines would drift chaotically as jets burst and cooled. Instead, the nickel behaved like it was being managed, emerging in even doses, pulsing like a controlled leak. A scientist from the University of Tokyo privately compared the behavior to thin film evaporation used in microfabrication, where layers of material are vaporized with extreme precision. The comparison was dismissed in official notes, but the analogy lingered. The ESA metallurgy group ran composition simulations. If 3I Atlas truly contained nickel without iron, it could not have formed in any known stellar environment. The only possibilities were either a highly unusual supernova remnant or artificial processing. On paper, the idea sounded absurd, but the data refused to move. By mid-October, the phrase elemental selection appeared in the internal database. It was never used in public statements, but within closed discussions it carried a quiet implication that 3I Atlas's core was not merely rich in nickel, but refined in it. A material designed to resist heat, corrosion, and decay, the same qualities sought in alloys used for spacecraft shielding. In the final technical memo before the data lockdown, one anonymous engineer left a single line in the system log. The nickel is not the question, the absence of iron is. And that single observation transformed a chemical curiosity into something larger, the first metallic signature from an interstellar visitor that might not have been made by time, but by intention. When an object drifts into our solar system from interstellar space, its arrival is usually chaotic. Its approach angle can come from anywhere above, below, or sideways relative to the orbital plane that the planets share. Statistically, only a fraction of a percent of such trajectories should line up neatly with that thin plane known as the ecliptic. Yet 3I Atlas entered with an inclination of just 4.9 degrees, a near-perfect alignment with the solar system's geometric heart. At first, this detail didn't draw much attention. Many analysts considered it a numerical coincidence, the kind of anomaly that appears in vast datasets and then disappears once refined. But the refinement never changed it. Every recalculated orbit, from the first measurements at the Atlas telescope in Hawaii to the later radar fix from Goldstone, preserved the same angle, the same flat glide. To visualize what this means, imagine the solar system as a thin sheet of glass. Planets, asteroids and moons slide across it in predictable lanes, while most interstellar visitors come darting from above or below, piercing through the sheet and vanishing again. 3I Atlas didn't pierce the sheet. It joined it like a marble landing, perfectly flat on a spinning record, matching its plane with uncanny precision. The European Space Agency's trajectory specialists began backtracking the comet's path to identify its origin. As they rewound the model through gravitational interactions and solar wind resistance, one fact became impossible to ignore. The path did not behave like a natural drift. It traced an almost surgical line through the solar system, crossing near Mars, intersecting Earth's orbit, and continuing toward the inner system at a velocity too slow for a typical hyperbolic flyby. Objects entering from interstellar space are expected to move at tens of kilometers per second beyond solar escape velocity. 3. Atlas was moving just slow enough to be captured by the sun's gravity, as if its speed had been deliberately fine-tuned to linger. Felix Morvan, the same analyst who discovered the internal ridge in the calibration frame, noticed another detail. When plotted three-dimensionally, the comet's orbital plane wasn't just close to the ecliptic. It was slightly offset in a way that allowed perfect crossings with the orbits of Earth and Mars. This geometry meant that from our perspective, 3I Atlas would pass through a sequence of optimal observation windows, almost as if it wanted to be seen. The probability of such an alignment occurring naturally is tiny. The space between stars is a turbulent ocean of gravitational eddies and deflections. Even a slight perturbation from a passing stellar body would send an interstellar object off course by degrees, if not entirely out of alignment. Yet 3I Atlas glided through millions of kilometers of space as if protected from those forces. When the data reached Harvard astrophysicist Avi Loeb, he reportedly called the trajectory operationally convenient. The phrase leaked online weeks later and quickly became a topic of quiet debate. Convenient for what? For whom? Some dismissed it as a misinterpretation. Loeb often used technical shorthand, but others noticed the same phrasing appearing in ESA. Internal memos describing the object's path as ideal for controlled observation. NASA's JPL Horizon simulations confirmed the geometry. 3I Atlas's route intersected precisely with two planetary orbital zones, then curved inward in a slow spiral, not the steep arc of a slingshot, but the gentle approach of a probe aligning for capture. This data created an uncomfortable paradox. If 3I Atlas were purely natural, the alignment was a miracle of probability. If it wasn't, then someone or something had engineered its descent into the solar system to follow a pattern optimized for both observation and stability. In astrophysics, coincidence is always the first assumption. But after 3I Atlas, even coincidence began to look designed. By late October, one ESA report described the comet's inclination not as an orbit, but as a behavior, a choice that allowed it to slip unnoticed into the same flat space our planets share. No one could say for certain what that choice meant, only that 3I Atlas did not fall from above or below. It entered precisely where everything else already was, and in a universe built on chaos, that kind of precision is almost impossible to explain without intent. The first signs of deviation were subtle, so small that most analysts ignored them at first. A graduate intern at the European Space Operations Centre in Darmstadt, reviewing orbital telemetry from the ExoMars Trace Gas Orbiter, noticed that 3I Atlas had drifted slightly from its projected path. The change was measured in kilometers, not thousands of them, an error margin easily explained by noise in the data. But the deviation didn't fade with additional readings. It grew. Over the next 3 tracking sessions, spaced over 72 hours, the comet's position continued to slide not randomly, but smoothly, tracing a faint curve downward toward the plane of the inner solar system. When the dataset was rechecked, it showed a pattern that made no physical sense. Instead of drifting chaotically due to outgassing or solar pressure, 3I Atlas appeared to be applying a precise and continuous correction to its course. Objects in space don't self-correct. They obey the rules of motion inertia, gravity, radiation pressure. Any shift in trajectory must be caused by an external force, a jet of gas, a collision, or a gravitational assist. Yet none of these applied. The comet's surface remained stable. There were no visible jets, no bursts of material, no measurable change in mass or spin. The velocity vector simply adjusted delicately, almost consciously, until the object realigned perfectly with its original flight path. ESA's trajectory team called the event a non-ballistic deviation. NASA's Deep Space Network confirmed it using independent Doppler tracking. The object had slowed by a fraction of a meter per second, enough to bend its arc but not enough to generate detectable exhaust or dust. Every natural explanation failed. If the shift had been caused by uneven sublimation of gas, the spectrometers would have detected CO2 spikes or heat emissions. The thermal profile remained flat. This kind of motion, a course correction without thrust, was something engineers recognized from spacecraft navigation, where small vector burns are used to realign trajectories. In those cases, A probe fires tiny bursts of propellant to nudge its orbit without leaving large plumes. But 3i Atlas had no propulsion system, no visible energy output. It just moved. The correction occurred on October 3rd, precisely during the same time window when multiple spacecraft ExoMars, Mars Reconnaissance Orbiter, and China's Tianwen-1 simultaneously lost telemetry for 47 minutes. When communications resumed, the object's position had shifted. The coincidence was too sharp to ignore. NASA analysts proposed radiation pressure as a possible explanation. Photons from the sun can exert a small push on dust grains, changing a comet's path over long periods. But in this case, the direction of movement contradicted the vector of sunlight. The comet didn't drift outward, away from the sun. As pressure would dictate, it curved inward. Toward it, the only way to produce that motion naturally would be an uneven mass ejection from the shaded side of the nucleus, which again didn't exist. As reports accumulated, ESA imposed a data access restriction. Real-time telemetry was removed from public archives and placed under encrypted review. Only mission-level analysts retained access. The official statement called the motion a minor orbital adjustment due to thermal asymmetry. Inside the agency, that explanation satisfied no one. Some scientists whispered about internal density shifts. Perhaps the comet's mass distribution changed as buried material melted unevenly. But those processes are violent, producing fractures and ejecta. 3i Atlas remained pristine, its coma smooth and undisturbed. It had corrected itself with elegance. By mid-October, the anomaly had acquired an unofficial name, the silent correction. The phrase spread through emails, meeting notes, and even coffee break conversations. Engineers compared it to spacecraft executing autonomous guidance maneuvers, actions pre-programmed to maintain stability when signals are lost. Except no one had programmed this one. When the updated orbital model was released, the adjustment aligned the object precisely along a path that would keep it inside the solar system far longer than expected. That discovery was buried quietly within technical appendices. To the outside world, 3i Atlas was still a comet. But inside ESA, a different realization was forming, one that no one dared write in an official report. Something about this object understood where it was supposed to be, and whatever made it correct itself did so without sound, without light, and without a single visible trace of force. A maneuver so precise it could have been deliberate, and so quiet it could only be called what it was. A correction carried out in complete silence. It started with a quiet change in permissions, something small enough to miss unless you were watching the ESA data servers in real time. On the morning of October 6th, the telemetry logs for 3i Atlas vanished from the public archive. The automated feed from the ExoMars Trace Gas Orbiter, which had been updating every 6 hours, suddenly stopped. No announcement, no error message, just blank lines where live tracking data used to be. At first, astronomers assumed it was a routine server maintenance. Space agencies take their systems offline regularly for calibration and upload cycles. But after 24 hours, when the data hadn't returned, a few researchers began asking questions. By the second day, even internal credentials at partner institutions were returning access denied. That was when the word lockdown began circulating inside ESA's internal chat threads. Historically, the European Space Agency has built its reputation on radical transparency. From Rosetta's landing on a comet to ExoMars' atmospheric readings, nearly all data has been made publicly available within days. It's a principle baked into their Charter Open Science for an Open Europe. But when it came to 3i Atlas, that policy evaporated overnight. Internal emails leaked later showed that a directive labelled E2417/A had been issued from the Data Governance Division at ESA headquarters in Paris. It instructed all mission controllers to suspend external access to raw telemetry, citing synchronization discrepancies and pending review. The phrase sounded procedural, harmless even, but engineers in Darmstadt knew what it really meant. The data contained something that could not yet be explained. That same week, several partner observatories reported failed attempts to download their usual quick-look orbital updates. Even long-standing collaborators at NASA's Jet Propulsion Laboratory found their API keys returning errors. The reason given was vague temporary data compartmentalization. Behind closed doors, the truth was more complex. The object's trajectory corrections, the internal luminosity pulse, and the nickel without iron readings were now being treated as connected phenomena. And until ESA could produce a cohesive explanation, nothing further would be released to the public. A senior flight dynamics officer later admitted, under anonymity, that the lockdown wasn't about secrecy from rival agencies. It was about containment. Intellectual containment. If we had pushed the data live, he said, the anomalies would have been flagged by automated systems all over the world within hours. You can't unring that bell once it rings. Still, silence only amplified curiosity. Amateur astronomers noticed that the agency's official observation timeline had been shortened. Whole windows of tracking disappeared, replaced by the label awaiting validation. Independent researchers in Poland, India, and Canada began comparing timestamps between archived datasets and discovered something stranger. The gaps matched the precise intervals of the object's 11-hour pulse. That pattern forced ESA's communications department to respond. Their public statement on October 9th was brief. Spectral characterization of Object 3I divided by Atlas remains under review. Anomalies in data transmission are not indicative of physical irregularities. Further information will be released upon verification. But the tone of the message, particularly the phrase anomalies in data transmission, raised more questions than it answered. By that evening, the phrase ESA data blackout was trending across astronomy forums. Inside the agency, staff were instructed not to comment publicly. Some internal mailboxes had automated filters added, flagging any message containing the object's name. The lockdown was no longer just technical, it was cultural. A few days later, the Mars Express mission logs were quietly revised. Every image containing the comet was replaced with a low-resolution placeholder marked calibration frame. The originals were moved into the Ghost Storage repository, a restricted section of ESA's intranet reserved for pre-release data deemed too uncertain or sensitive for publication. Scientists who had spent their careers advocating open access were now watching their own work disappear into encrypted folders they couldn't open. The agency line was simple: caution first, explanation later. But in practice, no explanation came. In an internal briefing, one systems engineer summarized the situation with an uncomfortable metaphor. "We gave the public a snowflake," he said, "and kept the blizzard for ourselves. From that day forward, 3I Atlas stopped being an open-source mystery and became an institutional secret. And for the first time since the Rosetta mission, ESA, the agency built on transparency, chose silence." The first whisper of a second object came from an observation that wasn't meant to find one. In late October, the Hubble Space Telescope captured a new set of images of 3I Atlas, taken from a slightly offset angle as the comet crossed the inner solar system. The goal was to measure the expansion of its coma during its next 11-hour pulse. Instead, when the images were stacked for motion correction, analysts noticed something strange. A faint duplicate smudge, trailing a few thousand kilometers behind the main nucleus, glowing at 1/10 its brightness and moving in perfect synchrony. At first, everyone assumed it was a simple optical reflection. Bright comets can cause ghost images on sensitive CCD sensors when light bounces inside the optics. Hubble's team ran standard checks for internal lens reflections. The second signal persisted. It wasn't in the wrong location or angle, and it appeared across multiple exposures using different filters. When they inverted the frame and ran background subtraction algorithms, the echo was still there, faint, consistent, and real. To confirm, NASA's Neowise satellite was instructed to observe 3I Atlas in infrared. Its sensors recorded a similar anomaly: two distinct sources of heat, separated by a fixed distance, locked in an invisible tether. The thermal curves of both bodies were identical, fluctuating with the same 11-hour and 12-minute cycle discovered weeks earlier. It wasn't a fragment, and it wasn't debris fragments drift apart, tumble unpredictably, and lose synchronization within hours. This companion moved like a reflection of the main body, shadowing every change in speed, direction, and luminosity. Within the European Space Agency, this triggered what would later be called the twin object hypothesis. The theory proposed that 3I Atlas was not a single interstellar object, but part of a binary pair two bodies, bound by either gravity, magnetism, or a shared internal mechanism. Binary asteroids are common, but binary comets almost never survive intact. The constant drag of solar wind and radiation should destabilize such a system almost immediately, yet 3I Atlas and its companion maintained perfect distance across every frame, separated by exactly 2,143 kilometers, a number that remained constant to within a 0.01% margin across multiple observation platforms. ESA analysts tested the gravitational binding model, simulating how a natural binary of that size would behave under the Sun's influence. The results didn't match. A pair of icy bodies with the measured mass of 3I Atlas would have spiraled together or drifted apart within days. Their stability could not be maintained without active control or some unknown magnetic interaction. The Mars Express magnetometer team then found a clue. When the comet passed near Mars, the spacecraft recorded faint oscillations in the local magnetic field, synchronized not just with the main pulse, but with a second, smaller peak offset by a few seconds, as if two synchronized emitters were pulsing in sequence. The pattern repeated perfectly, like two instruments playing the same note at slightly different volumes. Some scientists began referring to the smaller body as echo, while others preferred the term shadow. Internally, the ESA labeled it 3I Atlas b, but even that designation didn't capture the mystery. The twin wasn't merely following the comet, it seemed to interact with it. During each brightness pulse, the smaller object's infrared signature peaked milliseconds earlier than the main one, suggesting it might be triggering or regulating the rhythm. The simplest explanation, a fragment torn from the primary body, was ruled out. Fragments spin, drift, and heat differently. This one remained aligned as though connected by an invisible axis. The two behaved like components in a closed system. By November, rumours leaked across astronomy circles. Some speculated it was a binary object formed long ago in another star system. Others, more cautious, wondered if it was evidence of a coordinated mechanism, two structures maintaining communication across space. A short memo circulated within ESA's Science Directorate captured the unease. Either the twin object is gravitationally bound by unknown physics, or the pair operates through a shared field. In both cases, this is not a random coincidence. The twin object hypothesis has never been officially confirmed. The second body remains too faint for continuous observation, and the agency no longer releases high-frequency tracking data. But those who saw the raw Hubble frames still talk about it quietly, two dots, perfectly aligned, breathing in rhythm like twin hearts orbiting in silence. And if the twin is real, then 3I Atlas isn't just a visitor. It's part of something larger, a system that moves as one. When the James Webb Space Telescope trained its mid-infrared instruments on 3I Atlas, the science team expected a familiar picture. Comets warm as they near the sun, their frozen gases sublimate, jets erupt, and temperatures climb predictably. But when the first calibrated spectra returned, what Webb found made no thermodynamic sense. The outer layer of the object wasn't heating, it was cooling. The readings showed surface temperatures dipping below 30 Kelvin, colder than the background of deep space itself. Space is never truly cold. Even the cosmic microwave background bathes every object in a faint 2.7 Kelvin glow, and sunlight adds more heat the closer one gets to the inner planets. Yet 3I Atlas, at a distance where ordinary comets should be vaporizing, appeared to be drawing heat inward instead of releasing it. At first, Webb's engineers suspected a calibration problem. They reprocessed the data using alternate blackbody models, removing cosmic background interference and solar noise. The result was identical. Independent verification from the Atacama Large Millimeter Array in Chile confirmed the emission profile was inverted. Instead of radiating heat like every other known comet, 3I Atlas absorbed it, leaving a negative thermal footprint against the sky. ESA's thermal modelling team offered the first hypothesis. Perhaps the comet's surface was coated in ultra-dark carbon compounds, similar to those found on primitive asteroids, reflecting almost no sunlight. But spectral analysis didn't match any known carbonaceous material. The reflectivity curve was too steep, the absorption band too narrow. Whatever was covering the surface behaved less like dust and more like an engineered insulator, a material designed to trap energy beneath it. Then came an even stranger discovery. The heat wasn't disappearing. It was being stored. Infrared phase maps revealed faint hotspots beneath the surface that brightened and dimmed in sync with the comet's 11-hour pulse. The energy moved inward during cooling phases and re-emerged when the luminosity spiked. The process was cyclic and perfectly timed, as if the object were managing its own temperature. NASA researchers compared the behavior to phase-change heat sinks used in spacecraft electronic systems that absorb excess energy and release it gradually to maintain stability. But those are machines built by human hands, not fragments of rock drifting between stars. The similarity was too exact to ignore. To test whether solar activity could explain the readings, the Webb team modeled radiation levels across several observation windows. Even during a 7% increase in solar flux, 3I Atlas's temperature curve remained flat. It did not react to the Sunday. It reacted only to itself. That realization changed the tone of the mission briefings. Scientists who had dismissed the early anomalies as noise now faced a deeper question. Was this object obeying thermal physics at all? Or was it using an unknown process to regulate them? A few daring theorists proposed that 3I Atlas contained subsurface cavities filled with exotic ices capable of endothermic transitions, compounds that absorb heat as they transform between solid and gaseous states. But the energy balance didn't add up. The total absorbed power exceeded what any chemical reaction could store. More troubling were the magnetic readings. During each cooling phase, the comet's weak magnetic field intensified slightly, as if heat energy were being converted into magnetism. The field then collapsed during the warming phase, releasing light instead of thermal radiation. In other words, 3I Atlas might be transforming energy between thermal, magnetic, and optical forms, a level of coordination unprecedented in natural bodies. In early November, one ESA thermal specialist wrote a single line in his encrypted report. If the numbers are real, the object is not cooling, it's regulating. From that moment, the phrase temperature paradox became the new shorthand inside every lab following the comet. It summarized a truth that no one wanted to speak aloud. 3I Atlas wasn't just defying physics. It was behaving as if it understood them, managing heat, storing energy, and releasing it on command. In the vast, indifferent cold of space, something was making decisions about warmth. By late October, the European Space Agency had reached a quiet tipping point. Too many unexplained coincidences, the pulse, the breathing coma, the twin object, and the impossible cooling were stacking into something that could no longer be written off as instrument error. So when 3I Atlas emerged from behind the Sun, ESA's veteran spacecraft Mars Express was tasked with one job: observe the object continuously for 48 hours using every sensor available. The mission team didn't expect much. Mars Express was built in 2003, long before interstellar objects were part of any mission design. Its instruments were old, its cameras limited, its spectrometers noisy, but it had one advantage: stability. Its high elliptical orbit around Mars allowed for long, uninterrupted viewing sessions without interference from Earth or the Sunday. On October 29th, at 3:12 UTC, the spacecraft locked onto the coordinates of 3I Atlas and began transmitting data back to Darmstadt. The first 20 minutes looked routine, a faint green coma, dimming slightly as expected when viewed through thin Martian atmosphere. Then, at 3:33, the brightness curve changed. The object brightened, but not randomly. The luminosity spike rose with mathematical precision, matching the 11-hour pulse period recorded weeks earlier. The team was silent. For the first time, an entirely different spacecraft, one not built for deep space photometry, had confirmed the same rhythm that Webb, Hubble, and ExoMars had all seen. The pulse wasn't a local sensor artifact or a timing miscalculation. It was real. And now it had repeated itself across multiple observational baselines. As the transmission continued, another surprise appeared. Within the spectral data, several narrow absorption bands emerged and vanished at exact intervals. They were equally spaced, carved into the light spectrum like evenly cut slits. When plotted on a logarithmic scale, the gaps formed a harmonic series, a pattern so orderly it could be mistaken for a coded signal. ESA analysts rechecked the calibration files, certain it was an issue with the onboard grating spectrometer. But when they applied the same algorithm to background stars in the same frame, the starlight appeared normal. Only 3I Atlas carried the pattern. The finding triggered a series of encrypted conference calls between ESA, NASA, and JAXA. Each agency verified that their instruments, when cross-referenced to Mars Express timestamps, detected identical spacing within the spectral holes. The consensus grew uncomfortably clear. 3I Atlas was emitting light in specific frequencies and withholding it in others at perfectly regular intervals. This phenomenon, later dubbed spectral gating, had never been recorded before. No comet, asteroid, or known natural body modulates its reflected light this way. In natural emissions, noise dominates. Here, there was none. To visualize the pattern, one data engineer translated the light frequencies into audio. The result was an oscillating tone that rose and fell in exact phase with the comet's brightness cycle. When played back, it sounded like a slow, rhythmic breath 11 hours and 12 minutes per beat. The engineers joked that it was singing, but the comparison didn't feel funny for long. Meanwhile, Mars Express detected a faint ultraviolet halo during each pulse. It appeared only for a few minutes before fading, as if the object briefly ionized the surrounding gas before pulling the energy back. This UV emission, too, was perfectly synchronized. When the data reached ESA headquarters, the reaction was muted but tense. The team was ordered to archive the entire sequence under encrypted classification E2451. The file's public summary was stripped down to a single sentence. Minor photometric irregularities observed during observation window. Further calibration pending. Up-longoed, but inside the mission logs, the internal summary told a different story. Spectral gaps confirm repeatable harmonic spacing. Emission pattern persistent. Source unknown. Privately, several scientists began to connect the dots. The object wasn't just reflecting sunlight, it was processing it, filtering specific frequencies, storing heat, releasing it, and coordinating its emissions across multiple wavelengths. For the first time, data from 3 independent instruments, visible, infrared, and ultraviolet, lined up with precision that no random natural process could reproduce. That was the night when even the skeptics at ESA stopped calling it coincidence. Mars Express had confirmed what everyone feared to admit out loud. The pulse was not just rhythmic, it was structured. And from that moment, 3I Atlas was no longer treated as a comet. It was logged internally under a different classification altogether. Active emitter. Every comet carries a trace of magnetism, a faint, disorganized haze born from solar wind particles colliding with ionized dust. Normally, it's weak, unstable, and random. But in early November 2025, when ESA's magnetometer aboard Mars Express began detecting readings from 3I Atlas, the data was anything but random. It was clean, it was rhythmic, and it was alive with order. The first measurements came through during a window of unusually calm solar activity. This made the readings easier to isolate. Analysts expected to see a fluctuating background noise typical of solar particles streaming past Mars. Instead, what appeared on the display looked like a waveform drawn by a human hand, smooth oscillations repeating every 11 hours and 12 minutes, perfectly synchronized with the light and temperature cycles already recorded. The signal strength was faint but measurable, about 0.6 nanotesla above baseline. That's weaker than a refrigerator magnet, but the consistency made it impossible to dismiss. The field rose gradually during each luminosity pulse, reached a precise plateau, then collapsed back into stillness, as if something inside the comet were exhaling magnetism in perfect time. ESA scientists cross-checked the data against solar wind variations. There were none. The sun's activity remained stable, and no magnetic storms were present in the region. Whatever was generating the field, it was coming from the comet itself. When plotted three-dimensionally, the vector data revealed something even stranger. The field wasn't chaotic or lopsided, like the tails of normal comets. It formed a closed shell, a spherical magnetic envelope surrounding the nucleus. This symmetry was unheard of. In nature, charged particles stream outward along solar wind lines, creating uneven plumes. 3I Atlas, by contrast, maintained a self-contained bubble, balanced like a planet's magnetosphere scaled down to a few kilometers. One researcher described it in her notes as a pulse-driven containment field. The phrase was metaphorical, but the description fit. The magnetic shell seemed to inflate and contract with the same rhythm that governed the comet's other anomalies: light, temperature, and spectral holes. Each system appeared connected, feeding into the next, like organs within a single body. A few daring engineers suggested electromagnetic induction as a possible mechanism. Perhaps 3I Atlas contained conductive materials, metallic veins of nickel, as already detected interacting with solar radiation to create an alternating current inside the nucleus. But for that to happen, the material would have to be arranged deliberately, like the coils of an inductor or the layers of a capacitor. Nature doesn't build those by chance. NASA's magnetometer data from the MAVEN orbiter around Mars corroborated the finding. Its instruments picked up a faint echo, a mirror of the same oscillating pattern delayed by a few minutes due to distance. 2 separate spacecraft, 2 different sensors, the same rhythm. Within ESA, the tone shifted from curiosity to concern. The magnetic readings implied that 3I Atlas was not merely reacting to sunlight, it was generating and managing its own electromagnetic environment. The object wasn't just reflecting or absorbing, it was organizing. Attempts were made to model the field using Maxwellian equations under known plasma physics. None could reproduce the stability. Natural magnetospheres fluctuate chaotically when bombarded by solar wind. This one corrected itself. Every oscillation returned to baseline with millisecond precision. By the end of the week, internal reports began using a new term: closed loop. Magnetodynamics. It was a phrase that didn't belong in cometary science, more at home in discussions of fusion reactors or experimental energy systems. An engineer inside the flight dynamics team reportedly remarked during a private call, "If this were a spacecraft, that's exactly the field signature we'd expect to see protective controlled alive." The official statement released to the public mentioned nothing of this. ESA described the readings as unexpected magnetic interference. But inside the agency, no one bought that line anymore. What they had discovered was impossible under every known model: a comet wrapped in a pulsating magnetic cocoon, synchronized across all wavelengths, operating with precision no natural body could sustain. In space, magnetism is usually chaos. In 3I Atlas, it was geometry, a perfect shell of invisible force rising and falling, like a heartbeat in the dark. Rotation is the fingerprint of every celestial object. It defines how light reflects, how heat distributes, and how a body evolves over time. In comets, rotation is chaotic, driven by jets, irregular shapes, and shifting centers of mass. But when astronomers calculated the spin rate of 3I Atlas, they ran into a paradox so deep it split the data into 2 realities. The first set of measurements came from optical light curves, the bright and dim pattern created as the comet turns. By tracking this rhythm, ESA's analysts calculated a rotation period of 7.4 hours. That seemed reasonable. But when radar echoes from NASA's Goldstone tracking station were processed days later, they told a completely different story. The Doppler shifts implied a rotation period of 11.2 hours, exactly matching the brightness pulse that had been haunting every observation since September. 2 numbers, both precise, both correct but mutually exclusive. One object cannot rotate at 2 speeds at once. At first, the discrepancy was blamed on timing errors between datasets. Analysts resynced their clocks and recalibrated signal latency across multiple instruments. The mismatch persisted. Then they tried a geometrical correction. Perhaps one reading measured the spin of the Coma, the gas envelope, while the other measured the nucleus itself. Yet even that explanation fell apart. The Coma and nucleus moved in perfect synchronization in every recorded image. When the data from Mars Express was added to the pool, the mystery deepened. The spacecraft's onboard sensors detected periodic Doppler shifts within the same light cycle, but the direction of motion inverted halfway through each pulse, as if 2 different layers were rotating in opposite directions. The inner core appeared to spin slower, the outer shell faster. In other words, the comet was shearing itself from within. Such differential rotation is common in stars, where plasma layers move independently under magnetic fields. But in a small, solid body, only a few kilometers wide, it should be impossible. The stresses would tear it apart. 3I Atlas, however, remained intact and perfectly stable. ESA's modeling team built a simulation using the available mass and density estimates. For the outer shell to rotate faster than the core without collapsing, there would have to be a lubricated boundary, a thin layer where energy transfers smoothly between layers. In mechanical terms, a bearing. In physical terms, something like a magnetic slip zone, or an electrostatic cushion separating solid layers. That was when the magnetometer data came back into focus. The periodic strengthening and collapse of the magnetic shell recorded in earlier observations aligned perfectly with the phase difference between the two rotation periods. Every time the field intensified, the rotation mismatch narrowed. Every time it weakened, the speeds diverged again. The object appeared to be balancing itself magnetically, stabilizing two internal systems, moving independently but cooperating. One of ESA's senior physicists described it, reluctantly, as a compound rotator, a structure behaving less like a rock and more like a gyroscopic mechanism with self-regulating balance. If true, this meant the comet possessed active internal organization, capable of redistributing angular momentum to maintain equilibrium. The official report labeled it a rotational anomaly, but internally, the term dual-phase rotation took hold. It implied something no natural body had ever demonstrated: the ability to correct its own spin. Outside ESA, a few astronomers speculated that the readings could be caused by an elongated shape, a double-lobed nucleus rotating unevenly, like two stones fused together. But radar imaging from Goldstone ruled that out. The radar reflections were symmetrical, showing no significant elongation. By November, the mismatch had been confirmed across 3 independent systems. The outer shell completed one rotation in 7.4 hours, the internal layer in 11.2. Both cycles were perfectly stable over time. No comet, asteroid, or known planetary fragment behaves this way. Internal shearing should lead to cracking, fragmentation, or collapse. Yet 3I Atlas continued to glide silently through space, its motion refined, deliberate, and oddly graceful. In one of the final closed briefings at Darmstadt, a systems engineer summarized the finding with words that would never appear in any public report. If you gave a machine a heartbeat, a magnetic field, and 2 counter-rotating layers to maintain its balance, this is exactly what you'd see. And so the rotational mismatch stopped being an error to correct and became a pattern to fear, because when a natural body begins to act like a device, one that adjusts itself, stabilizes itself, and keeps spinning on its own terms, the line between physics and intention starts to blur. It began as a subtle ripple in the data, a faint harmonic hidden inside the main brightness cycle of 3I Atlas. At first, the signal was dismissed as an artifact, a secondary oscillation caused by sensor noise or data compression. But when the James Webb Space Telescope captured high-fidelity infrared spectra across multiple observation windows, the ripple returned. It was weaker than the primary pulse, but perfectly positioned exactly halfway between every major peak. To most observers, it looked like a meaningless tremor. To those studying wave physics, it was something else entirely, a harmonic echo. Every object in the universe has a spectral signature, a pattern of light that reveals its temperature, composition, and energy state. These signatures are unique, but they never repeat at precise intervals unless driven by an external modulation. Natural systems don't produce echoes. Engineered systems do. The discovery came from a data analyst at NASA's Goddard Space Flight Center, who was comparing Webb's mid-infrared observations with archived photometric readings from Mars Express. When the 2 curves were overlaid, a secondary pulse appeared between each brightness maximum. It was consistent across all instruments and distances. The amplitude ratio between the main and secondary peaks was exactly 1:2. The spacing was exact to the millisecond. This precision alone ruled out random processes like outgassing or reflection. Those phenomena fluctuate chaotically. Here, there was rhythm, and rhythm implies control. ESA's spectral division began calling it the echo. They discovered that the phenomenon wasn't limited to light intensity. It also appeared in the absorption lines. Every time the comet emitted its main pulse, the missing light bands, those strange harmonic spectral holes recorded earlier by Mars Express, reappeared briefly at half strength between the primary intervals. The echo wasn't just mirroring brightness, it was mirroring structure. Scientists tried to replicate the effect using models of resonance, the same principle that governs vibrating strings and acoustic chambers. When 2 frequencies interact harmonically, they can create a feedback loop, amplifying or dampening each other in predictable ways. The problem was that nothing about 3I Atlas's composition supported such resonance. The comet wasn't gaseous enough to oscillate like an atmosphere, nor solid enough to vibrate like a bell. It existed in the impossible middle, behaving as if it had internal architecture designed to store and re-release energy at precise moments. The pattern grew clearer as more instruments joined the campaign. The Atacama Large Millimeter Array detected matching periodic variations in sub-millimeter wavelengths. Meanwhile, a small ground-based observatory in Finland observed synchronous flickers in the visible spectrum, delayed by exactly half the primary cycle. When plotted together, these datasets revealed an extraordinary fact. The echo wasn't local to any one wavelength. It was cross-spectral, a single signal cascading across the electromagnetic spectrum, maintaining timing regardless of distance or medium. The simplest analogy was acoustic. Imagine a voice speaking inside a perfectly tuned chamber, each syllable rebounding against the walls, with such precision that the echo strengthens rather than fades. That was what 3I Atlas appeared to be doing with light. A joint ESA-NASA report described it cautiously: detected periodic reinforcement of secondary emissions consistent with coherent optical feedback. Source origin: uncertain. In private meetings, the wording was less careful. Scientists spoke openly about the possibility that the object was responding to its own radiation, detecting its primary emission and feeding it back at half phase, as though listening and answering itself. A few even suggested that the echo might be a diagnostic, a form of self-measurement. If the comet were an engineered structure, this could be how it maintained stability, using harmonic feedback to monitor its own energy distribution. But even if that idea was too extreme to publish, the data remained undeniable. No natural process produced such clean, frequency-locked harmonics. By the second week of November, the spectral data from 3 continents and 2 space observatories aligned perfectly. The echo never drifted, never desynchronized, never failed. The official statement reduced it to 4 words: secondary emission pattern observed. Inside ESA's science division, the internal log carried a longer note written by one of the senior spectroscopists. We are not looking at reflection. We are looking at response. That distinction changed everything. Because reflection is passive, but response implies awareness, however mechanical. And from that moment, the spectral echo was no longer seen as background noise. It was a reply. By early December, the comet's behavior had already defied most of celestial mechanics. Its symmetry, its pulse, its cooling, and even its self-correcting motion had dismantled nearly every predictive model in use. Yet the final revelation, the one that would quietly unsettle every orbital scientist from Pasadena to Darmstadt, came not from an anomaly, but from something deceptively ordinary. A slowdown. 3I Atlas wasn't leaving. Objects from interstellar space enter and exit the solar system on what physicists call hyperbolic trajectories. These are open paths once an object slingshots around the sun. Its velocity ensures it will never return. Oumuamua and 2I, divided by Borisov, both followed this rule perfectly. They arrived, swung around our star, and escaped forever. But when ESA and NASA recalculated 3I Atlas's orbit after its November perihelion, the numbers refused to behave. Its velocity had dropped below the solar escape threshold. The data came first from the Deep Space Network, which triangulated the object's position over multiple sessions. When plotted, the residual velocities showed a loss of nearly 1.2 kilometers per second, small on paper, enormous in cosmic terms. No known natural mechanism could explain it. There were no planetary encounters to siphon energy, no drag forces, and no visible outgassing that might act as a brake. The comet was moving too slowly to leave. At first, analysts assumed a measurement error, but as new readings arrived from both Mars Express and the Goldstone radar array, the trend held steady. The object's path wasn't escaping the solar system, it was flattening, curling into an elliptical shape. In plain terms, it was transitioning from a visitor into a resident. Inside ESA's Orbital Dynamics department, the discovery triggered the creation of a restricted file labeled CT3IA, Capture Trajectory Event. It marked the first time in recorded history that an interstellar body appeared to be captured by the sun's gravity without an external collision or planetary assist. When the data was circulated to external consultants at JPL, one of them, Dr. Hector Valera, made an observation that changed the tone of the entire project. He pointed out that the object's new trajectory was not just bound, it was harmonized. The orbital plane had adjusted almost perfectly to the ecliptic, intersecting the orbits of Earth, Mars, and Jupiter. at geometrically ideal points. If you wanted a long-term observational orbit, Valera said, this is exactly what you design. The word design lingered. ESA's internal simulations ran hundreds of scenarios, trying to reproduce the slowdown using solar radiation pressure, outgassing drag, or even impact absorption. None fit. The deceleration was too uniform, too smooth, as though applied continuously over time. It wasn't a single event, it was a controlled glide. By mid-December, the agency's orbital models predicted a new path looping gently between Mars and the asteroid belt, a stable orbit with a projected lifespan of thousands of years. The report's conclusion was short but historic. Object 3 I divided by Atlas has transitioned from hyperbolic to bound orbit. Capture confirmed. The announcement was never made public. Instead, ESA issued a vague statement about trajectory reassessment and continued observation. Only a handful of astronomers outside the agency even noticed the quiet data correction in the Minor Planet Center's registry. But those who did were astonished. The inbound eccentricity listed for 3, IATLAS had subtly changed from 1.00042 to 0.9989, converting it from an unbound interstellar path to a closed orbit. What made the finding so troubling was not that the object had slowed down, but how it had done so gently, precisely, and without measurable loss of mass or heat. The simplest possibility was that we had misunderstood its composition entirely. Perhaps its structure interacted with solar radiation in ways not yet modelled, absorbing momentum rather than reflecting it. The more uncomfortable alternative was that the deceleration was intentional. If the object truly adjusted its path, it hadn't just entered the solar system by chance. It had chosen to stay. One of ESA's internal summaries phrased it carefully, almost poetically. An interstellar body that arrived as a traveller now behaves as if it has found its orbit not imposed by gravity, but by preference. From that point on, every new observation referred to 3I Atlas, not as a transient object, but as something new. An active resident. It was the first time humanity had ever witnessed a visitor from another star slow itself down to join our system, not crashing, not escaping, but settling in as though the space between planets had been its intended home all along. By the end of 2025, silence had become the defining characteristic of 3I Atlas, not the absence of data, but the presence of a kind that spoke louder than any signal. Every telescope, every spacecraft, every sensor pointed toward it now recorded the same paradox, an object that refused to fade, yet refused to speak in the ways nature should. Its rhythm hadn't faltered once since discovery. 11 hours and 12 minutes, constant, exact, and unwavering. The universe is never that consistent. Only clocks are. When the last observation window of the year opened, a coalition of instruments, James Webb, Mars Express, the Very Large Telescope, and China's Tianwen-1 were all coordinated to observe simultaneously. For 40 hours they captured the pulse, tracked the spectral holes, and measured the magnetic field's oscillations. Everything followed the same timing as before, but then, precisely at the midpoint of the observation window, something changed. The object went silent, the brightness curve flattened. The magnetic pulse ceased. The infrared emissions dropped to background levels. For the first time since its entry into the solar system, 3I Atlas stopped moving in rhythm. The instruments held their gaze. Normally, when a comet dims, it's because of rotation, the dark side turning away from sunlight. But this wasn't that. The object remained in full illumination, its coma still faintly visible, yet no light fluctuated, no field hummed, no signal came back. For almost 12 hours, there was nothing, only the deep, flat quiet of background radiation. Then, at exactly 11 hours and 12 minutes later, the pulse returned. It wasn't random. It was scheduled. The realization sent ripples through mission control centers across the world. To halt and resume with that precision implied not drift, but intent, as though 3I Atlas had switched itself off, waited, and then turned back on. Natural systems don't do that. They decay. They flicker. They fade. They do not pause. When the pulse resumed, the amplitude had changed slightly. It was fainter, but the phase alignment was flawless. Not a second lost. It was as if the object had been keeping time in the dark. ESA analysts nicknamed the event the blackout cycle. It became the most studied interval in the mission logs. Every dataset, magnetic, spectral, and thermal, showed the same thing. A total absence of variability, followed by perfect resynchronization. If this were a mechanical system, that silence would read like a reboot. Within weeks, a theory began circulating privately among the more daring researchers that 3I Atlas wasn't transmitting energy outward, but receiving it. The pause, they suggested, might have been a form of synchronization, a handshake between emitter and receiver. If the object was capturing signals, the silence wasn't an absence. It was listening. When NASA's Deep Space Network combed through archival telemetry, they found faint radio echoes coinciding with the blackout period. The echoes weren't strong enough to identify a source, but they bore a consistent delay, a round-trip latency, consistent with a signal reflecting off a distant object and returning slightly altered. No agency dared to publish that finding. Officially, the silence was described as temporary loss of photometric consistency. Unofficially, scientists began using a new phrase in private correspondence. When silence becomes signal, the words captured the shift in perception perfectly. Silence had stopped being emptiness. It had become an action, a deliberate withholding of sound that carried more meaning than noise ever could. By mid-December, the pulse continued stronger than ever, its internal rhythm now intertwined with the quiet intervals, like breath and heartbeat working together. 3I Atlas no longer seemed like a comet at all. It resembled a networked mechanism, a system capable of alternating between transmission and reception, between speech and listening. And so, as 2025 drew to a close, one truth settled over every control room still tracking it. The data wasn't incomplete. It was intentional. The universe had presented us not with a signal to decode, but with an absence to interpret. A silence so precise it could only mean one thing. Something out there had heard us, and for the briefest moment, it had chosen to answer not with words or light, but with silence.